Hi, my name is Sarah Cutts. I'm a PhD student at Indiana University. Here I'll be discussing how brain behavior correlations and fMRI functional connectivity vary over time. Functional connectivity can be easily computed by taking the correlation between the bold signals of two brain regions. Then taking these correlations for every pairwise combination to create a functional connectivity matrix that you can average over a group or look at individual subjects. Individual subjects seem to differ from each other, and these differences can be utilized towards behavioral and phenotypic predictions. However, it's becoming more clear that it may take thousands of individuals or several samples within a handful of subjects to actually achieve decent effect sizes and reproducibility of behavioral associations. Now, most of these studies usually look at full functional connectivity, but prior work suggests that individual differences vary within a scan, and so it may be worth looking at how different moments in time relate to behaviors rather than looking at the full pattern. Edge time series is one approach that allows you to look at this frame-wise information. It does this by taking functional connectivity and decomposing it into each individual frame's co-fluctuations. This is computed by looking at the product between the bold signals of a pair of brain regions at each time step to create a co-fluctuation time series that you then compute for every edge. Functional connectivity can then be computed from the average across edge time series, making edge time series an exact decomposition of the connectivity pattern that we normally study. Now, from edge time series, it's become clear that there are a few moments in time with really high co-fluctuations that when you take the root sum squared across all edges for these time points and plot it as RSS shown below, there are a few moments in time with these high co-fluctuation magnitudes that contribute more towards the average signal that we're seeing from full functional connectivity, even though these are only a few moments within the scan compared to the rest of the duration. These moments are much more similar towards the full connectivity pattern. But as can be seen from this video, these different frame-wise co-fluctuations vary significantly and don't necessarily always look like the full functional connectivity we're used to studying. They have very structured dynamics that actually emphasize different signals across functional networks, but we often don't see this when we're studying the full pattern. And these might be relevant towards behavioral prediction. As I said, if you take the average across edge time series, you get functional connectivity. But a similar approach, looking at the binarized nodal time series, if you take the agreement across that, you get a nearly identical component as functional connectivity that can then be utilized towards behavioral prediction because binary data is much easier to work with. Now, most of what I've been showing looks at the full scan session, but you can take individual moments in time and reconstruct them through this agreement matrix to create a connectivity component that you can analyze. Now, these different frames that you're selecting can be selected based off of different criteria of interest. So for instance, if you have the root sum squared value that I mentioned previously for the high amplitude co-fluctuations in edge time series, you can sort these moments and select the frames that contribute the most towards the high RSS values and those that contribute the least, and then analyze those components separately. Or you can compare each of the time steps to a template of interest that, say, emphasizes co-fluctuations within or between different functional systems, and then analyze the components that are produced from the top percentage of frames that you select. Or you can create your own template and select frames that match any criteria of interest that you'd like, create a component from that, and then analyze it similarly to functional connectivity. Here, we looked at 352 subjects from the Human Connectome project. They each had 4 15-minute resting state fMRI scans, and we selected 58 different behaviors that we then performed optimizations with simulated annealing 100 times per behavior with 80 training subjects, 20 testing subjects for each of these iterations to investigate how behavioral correlations relate to RSS amplitude within a scan session, therefore how much they contribute towards the full scan, as well as determine how targeted selection of time points from these optimizations perform in relation to full functional connectivity. Now, if we just take the RSS values of the frames and then break them up into decile bins, we can then look at how frames relate to different behaviors. For this figure, you can see that the bins are sorted based off of RSS amplitude, with the first bin showing the highest RSS values and the last bin showing the lowest. And here we see that different behaviors have stronger mean brain behavior correlations in the top decile frames, while others load more onto the mid or low amplitude frames that are less seen in full functional connectivity. Looking at the full functional connectivity pattern itself, we can see that these behaviors that load more onto the higher amplitude frames do indeed show a stronger relationship in full functional connectivity to these different behaviors than the ones that load onto the mid or low. And these can be clustered into different groupings based off of their RSS loadings. Now, that was taking an approach related to deciles of a predefined category such as RSS, but you can select time frames based off of different criteria that you can then optimize. For instance, here we can optimize a template that selects time points with similar patterns of activity, and then relate each of these to the behavior of interest to find the optimal templates. In this example, we have an initial template that's completely randomized. We find the similarities with that template between all of the time steps, filter the top 10% of frames that look similar to that template, create an agreement matrix across that to create a functional connectivity component for every subject, then correlate every edge of this component to a behavior for a brain behavior correlation map that then is compared to the previous iterations of the template to determine whether or not it improved performance or decreased performance. And then from this, we can accept the templates that did better and then randomly permute those in order to send it through several iterations of the optimization. For this example, we're looking at specifically the behavior of vocabulary. And here, over 10,000 iterations of this template approach, we can see that the mean brain behavior correlations of the components that we filtered did significantly better than full and initial in terms of their mean brain behavior correlations. In the testing set from the cross-validations, we see some of the cross-validations performed better, but the story is a bit messier. But if you actually look at the individual cross-validation brain behavior correlation maps, you can see between full and initial, the similarities between training and testing sets are much lower than what you actually see from the optimizations, which show a much stronger similarity and reproducible results between those groups. If you look at this for every cross-validation, you can see significant improvements of transfer between the training and the testing sets in terms of the brain behavior correlation patterns for the optimized templates as opposed to the full and initial. Now, if you break down the edges into positive and negative edges from the training set, you can see that we actually also see a significant improvement of brain behavior correlations going in the valence direction that they were heading in for the training set. And this is for the optimized compared to the full and the initial templates. Now, looking at all behaviors, we see similar findings. And here we can see with these purple behaviors that each of these purple behaviors highlighted have a significant improvement in the similarities between training and testing set behavioral correlation patterns, as well as significant improvements in mean brain behavior correlations for positive and negative edges above that of full functional connectivity. These patterns can then be mapped onto which RSS templates they mainly load onto, and they're distributed across the time series in terms of different RSS amplitudes, but do tend to load more onto the higher amplitude frames than others. But when looking at the similarity with full functional connectivity, it's still much lower than what you would see from high amplitude events by themselves. We can also look at the temporal information of what moments in time are actually selected from these separate behaviors based off of when the template filtered. So looking at one subject across multiple cross-validations in which they were a testing subject, you can see how often the template filtered for those moments in time. Looking at the initial template, it's a pretty wide distribution of where the filters were pulled from. But looking at the optimized templates, we actually see moments in time that are significantly greater above a null when frames were often selected for that subject across optimizations. If we take all of the significant frames for an example subject across all behaviors, there is an overlap of different moments in time where multiple behaviors seem to load onto. Compared to a null, these moments in time that have greater significance in behavioral overlap also tend to show higher levels of RSS amplitude and significantly higher levels of similarity to full functional connectivity, as well as no differences in motion. In summary, the time points sorted by RSS amplitude showed distinct behavioral characteristics, where different behaviors load onto different amplitude frames. Optimizations using simulated annealing found that templates for filtering time points showed greater similarity between training and testing sets in terms of their behavioral maps, as well as a greater magnitude of positive and negative edge weights. Time points that improved behavioral correlations across RSS amplitudes did seem to load more onto higher amplitude frames, but overall did not significantly look similar to full functional connectivity, as did the moments in time where multiple behaviors overlapped. Thank you.